Hello, pre-calc. I wasn't expecting another AMI day, and I don't think you all were either, but beside the point, we are on a kind of a time crunch in terms of like covering content because I did want to be done with reviewing the geometry stuff before we started Trig by Thursday. So, yay! That last page of notes in your note packet will be extra helpful here. I'm only going to touch on a few of them, but all of the guided notes are already on the Google Classroom too. So if you're wanting to look through some more examples, just so you can get a better idea of it. So when we do start Trig, you're not just kind of like, I guess, scrambling for it, then by all means, look through them. But I was going to give homework on it too, but if I think you'll get the idea and I wouldn't want to be a dead horse in. So anyway, we're going to start the Trig stuff coming up on Thursday, hopefully, when we get back, knock on wood, because honestly, it's better to teach there and, it gets better stuff, but side point. Let's talk about the inverse trig functions, kind of. Note the word function isn't really used here because we haven't really discovered trig functions yet. Yes, we've done sine, cosine, tangent, but we haven't looked at f of x equals sine of x yet. But what is the inverse trig function? Well, if you use sine inverse on a ratio, you're going to end up getting an angle. So typically, you can only use sine, cosine, tangent on angles because sine of a certain amount of degrees equals something over something. So it can only be used on angles. So what if you want to find the angle? Well, that's when you use your inverse sine. Or arc sine is also another name for it. You might see it that way too. So sine inverse being sine to the negative first. Not 1 over sine, because 1 over sine means something completely different than sine to the negative first. Yes, negative exponents do flip your fraction and stuff, but this is something different. And that's why usually arc sine is the typical route to go for certain professions. Like engineering usually uses arc sine, so that way it doesn't get in the way of doing that. But let's look at an example. The very first example from the notes, actually. So you want to find x, and you have the opposite side to x and the hypotenuse because it's on the other side of the right angle. Then sine of this angle x that we don't know yet is equal to the opposite side being 25 over the hypotenuse being 24. So then in order to find x, you want to use sine inverse, punch that into the calculator, of 15 over 24 or 3 over 8. I simplified the fraction. Doesn't matter, you get the same answer regardless. So you should get an angle of about 38.7 degrees. And that's all there is really to it. We do the same thing with cosine and tangent. And this works perfectly for angles. So only for triangles or for triangles, not angles, but triangles. But that's why I have a whole thing about misconceptions on this part of the board. And I'll go through that soapbox in a second, but let me ask you question number 1. How precise do you have to be when finding angles? It depends on the context, obviously, but when would you need to be extremely precise when you find angles? Now, this is actually going to be a follow-up to our next lesson on Thursday when we actually start trig, because we're going to get to degrees, minutes, seconds, and actually my career choice, astronomy, you actually have to be extremely precise when you're looking at stars because they move millions of light years away by the second. So actually, if you look at NASA data, the angles are actually changing, unless you're looking at the RA index. But you can't use astronomy anymore to find precise angles. You actually have to find another profession or scenario where you are finding a very precise angle. So I guess question 1, just to reiterate, is what scenarios other than astronomy do you need to be very precise when finding angles? And why would that matter? So what would be a consequence of not having a precise angle? All right, that's question 1. So question 2 will come out later, but now let's talk about some misconceptions. So inverse functions, if you remember from when we actually did inverse functions where you flip-flop your x and y and solve for y, there's also some other hand-wavy stuff that we didn't go that much in detail with because we were already pressed for time. But if you remember that conceptually, the domain and range flipped because you're flipping all your x's and y's. But also, let's take the basic quadratic shape, right? You had that little U shape, right? Now, in order to have an inverse function, it would need to pass the horizontal line test, if you remember. Now, this bad boy didn't have pass the horizontal line test, did it? But usually it would need to, right? Well, that's why whenever we, the inverse function, if you remember, also flipped across x. So the inverse function was supposed to look something like this. However, that wouldn't be considered a function because it would fail a vertical line test, which is why we would get rid of half of it so that it would pass the horizontal line test and the vertical line test. And that's how we get the square root function, right? Because the inverse of your quadratic x squared is square root x. And even better, moreover, if you compose the two functions together and they're inverses of each other, you should just get x. So f inverse of f of x should just give you x, which is why when you square root x squared, you get x. That's what composition is. Or if you square root, you get x, because that's what inverses do. Whenever you compose them together, f of g of x, you should just expect to get x. Now, why am I going on this soapbox when talking about sine? Well, sadly, we haven't talked about the function sine of x, so f of x equals sine of x. But if you think about this, there are restrictions on the sine inverse of sine of x equal x. Do they just cancel out? Well, yes and no, depending on the circumstance. We're talking about just triangles. Yeah, they cancel because triangles, usually angles, are restricted to be less than 90 degrees. But what if your angles are negative or positive? So the measured angle can't be positive or negative or over 90 degrees. Certainly your orientation can, because if you're talking about angles, if you're going this way, it's positive. Going this way, it's negative. So it does work. But there are restrictions on it. And the reason why is, let's take a look at f of x equaling sine of x. This is actually what the graph of that looks like. And we're actually going to graph these bad boys later on in the semester. But I'm just giving you a little hint. In order to have an inverse function, it needs to pass the horizontal line test. Does that pass the horizontal line test? No. And why? Well, try to draw a horizontal line, it strikes many different places. So in actually order to get an inverse trig function, because every function should have an inverse, you actually need to kind of chop off your domain a little bit. Well, where? You can chop it off anywhere, hypothetically. But usually, conventionally, you want to try to chop it off to where you get the most for your bang for your buck to pass the horizontal line test. And usually 0 is a good number to have in your domain too. Like every function should have 0 in their domain, except 1 over x. That's like the one thing it doesn't have, but anyway. So what you need to do is, typically, we're just going to chop it off the domain until it passes the horizontal line test. We're going to chop a little bit off over here too, so that it does have the horizontal line test passed. And what are those values we chopped off at? Well, we're actually going to be talking about radians on Thursday, hopefully when we get back. But for all intents and purposes, a radian and a degree do have some similarities, and they have a conversion method. So this would be technically pi over 2 radians, which is equivalent to 90 degrees. So we are cutting it off at 90 degrees. That's good. It does include 90 too, because sine of 90 is 1. Punch it in your calculator, you'll get that. But try doing sine of 91. It'll give you a domain error. However, what about over here? Well, this is chopped off at negative 90 degrees. If you want, if your calculator that you have has sine and cosine and stuff, try putting in sine of negative 90. You should end up getting negative 1. If you're in degrees, of course, you got negative pi over 2 if you're in radians. So, but those are the restrictions on the domain, and they do include it. Now, question number 2 is going to be, try to research what your domain restriction for cosine would be. It's not negative 90 degrees. No, that's not cosine. And it might take you doing a little bit of research, but don't go too deep into it and get yourself confused and scared. But try to figure it out, because the graph of cosine is similar to sine. And try to find the domain in degrees, because we haven't talked about radians yet, unless you want to go down that rabbit hole and you keep getting interested in this stuff. But also tangent has a restriction too. Don't worry about tangent, that's weird. I'm not going to go on a tangent about it. But question 2, formally on the Google form, is going to be, what domain restrictions does cosine have? And you could just keep trying to plug in stuff into the calculator too to find out. And you might be interested in that, because it is interesting. Anywho, you got any questions, email me. Make sure to like, comment, and subscribe. I'm trying to go viral, I need my money. Okay, bye.